So looking at some properties of chords, tangents, secants, how they work, and getting some segment measures. First thing we're going to do is start off, I think we have talked about this before, but it's a good reminder. If we have a tangent line to a circle, such as that picture on our right-hand side where it touches the outside circle at one point, and it's tangent to the radius, so I can say that the tangent line touches the radius, I can say it is going to be perpendicular to that point of tangency being that point P where that tangent line is touching the circle. So the converse is also true. Converse being, if I'm looking at the statement, I'm rearranging the order of the statement. So a line through a point on a circle I know is tangent if and only if it's perpendicular. So it's tangent if it's perpendicular, and it's perpendicular if it's tangent. Okay? And just a little vocab here, it says tangent lines that meet two circles are called common tangents. Okay, so I know this is approved. Read through this. We're going to get through it. Good review for the final. Taking a look at the right-hand side, we have CD and CE are tangent. So here's our point CD and CE. Those are tangent to circle A. And we're going to prove, our goal here is to prove CD and CE are congruent. Okay, so we're proving that statement that we had up above. So those would be called common tangents. They meet, and we're trying to prove that these two lines that are going to be congruent. Okay, so we have CD and CE are tangent to circle A at those points. That's our given. Remember, you're always starting your proof off with your given. And then it's telling us to draw in. So if these weren't here, they're saying, well, we're going to draw in AE, we're going to draw in AD, we're going to draw in AC. I already did that for you, so we had the picture. And our reason here is through any 2 points, there is a line. So now it's saying ADC and AEC are right angles. So ADC is here, AEC is here, and it's saying that they're right angles. Well, I'm taking a look. I have a radius and a tangent line, and they are meeting at those points D and E. So I can say, for my explanation, a radius and a tangent, they will meet to form right angles. So I knew it was a tangent line from the given. I know a radius goes from the center to the edge of the circle. So I know those have to be right angles. So if I look at the triangles, I know that those have to be right triangles because any triangle with a right angle is a right triangle. Okay, so continuing on, we have AD is congruent to AE. So AD, AE, those are the radii of the circle. And we know that all radii are congruent. And AC is congruent to AC. That was our reflexive property. And so if we take a look, we have now right angles, right triangles, and 2 congruent statements. That does allow us to prove our triangles congruent. If we look back up at our picture, we get a case of hypotenuse leg. So I have the right triangles, and we said anytime we're doing a hypotenuse leg proof, we always have to state that they're right triangles. That's why we have that step 4 in there. And that's also why if we only have 2 congruent statements, that's okay. This was the important stuff. We needed right angles, right triangles, and we have our 2 congruent statements, which allows us to prove our triangles congruent by HL. And then our favorite step, once our triangles were congruent, we could always say any of the parts were congruent by CPCTC, standing for corresponding parts of congruent triangles are congruent. So we have here 2 tangents. What we have just proven actually is our 2 tangent segments to a circle from a common exterior point. We have just proven that they are congruent. Okay, so we had our two common tangents. They're both tangent to the circle, and they were coming from this exterior point. So find one exterior point, draw a tangent, draw a tangent. We have just proven then that these have to be congruent. Okay, so using that concept, knowing that if I have common tangents, they are congruent, we're going to use this picture, use some of the labels, and we're going to find the length of DE. So in the end, I want to figure out how big this entire segment is. Okay, starting with this picture, I'm going to start with CV. CV is tangent to the circle at point B. I also know that CV and CF have to be congruent because these are those common tangents from that exterior point. So if this length for CV is 2, then CF is 2. They've told me all of EC is 6. So if I know that that's whole thing is 6, I found that little part of 2, I'm left over with 4. Okay? If I use that segment, EF and EG are tangent lines, and they're tangent from that common exterior point. So that means EF and EG must be equal in length, saying EG has to be 4. Okay? If I go down to this segment on the bottom, CD, okay, I know the whole thing is 5, and we know that that little part is 2. So again, if I took the whole length, subtracted out the part we know, we're left with 3. So from D to E, I know is 3. D to B is a tangent to the circle, just like D to G is a tangent to the circle, and they both come from point D. So that means those have to be congruent. So if I'm trying to find the length of ED, I've just found those two little parts that I needed to know their lengths. So that means DE must be a total of 4 plus 3, or I can say DE has a length of 7. Okay, so we're going to come up with a couple of different formulas, and this is all based on similar triangles. We'll take a look at that aspect a little bit more in class, but the formulas that we need to be aware of and be able to use will help us find missing lengths of chords for this one, for instance. So our chords, as long as they're intersecting, and we take a look at this picture, I can tell you we're going to get the property A times B is equal to C times D. So it's saying I'm going to take the chord and I'm going to take the parts of the chord and multiply them, take the other parts of the chord and multiply them and set them equal. So keep in mind what we're saying here is we're not saying the chords are equal. Okay, chords, and maybe that's something that you want to write down to yourself. Chords are not necessarily equal, but I know that that property will be equal. Their parts multiplied will be equal. And again, that comes from similar triangles. Just real quick, I could show you that these triangles here would be similar. We could prove it by angle. And if that's the case, similar triangles have corresponding parts that would be in proportion, which would give us this property. Okay, if we use this idea, so if I'm down here on this picture, I'm going to maybe label one of these chords. And remember, I'm going to have A and B on one chord. I'd have C and D on the other chord. And it's saying I can take those parts and multiply them. So A times B equals C times D. Okay, so we're going to have 6 times X is equal to 4 times 12. So 4 times 12, we're going to have 48. And to get X, we're going to divide through by 6. And we're going to see X has a value of 8. So again, you can see if you add them up, those chords are definitely not going to be equal, but they, I will say, will be in proportion. Okay, so 2 more formulas that we get. So if I'm trying to find the lengths of secants, so this looks like a picture that we did before where we were finding the angle on the outside. Okay, different though this time because we're not finding angles, we're finding segment lengths. So same idea, I have a picture that has 2 secants and I want to find their segment lengths. The way I like to think about this is if I can think the outside part of the segment times the whole segment, or whole secant, is equal to the outside part of the secant times the whole secant. And when we're thinking whole, I want you to think add. You want to remember that in order to get the whole length. So if I look at that top secant here, the outside section of that secant, outside the circle, is A times the whole thing, and we said think add, so I could say A plus B. And we go to the bottom one. The outside section is just that section of C, and then to get the whole thing, I'm going to get C times D. I'm sorry, C plus D. Always thinking add. So outside times the whole. Right? Similar picture when we get this on the bottom. Notice what we have. The difference here is we have secants up on the top, and on the bottom we have a secant and a tangent. So you can always use that idea of saying outside times the whole. That will work no matter what. It's just with the tangent line, the outside part is the whole part. So you could still say outside times the whole if you want, keep it simple. You could also say to yourself, when you have a tangent, it's always going to be the tangent length squared, right? Because if I do outside times the whole, I'm saying A times A, which is A squared. So secants will always have that property, outside times the whole. Tangent would have that property, tangent squared. Okay, so if we were to set this up for this picture, the outside part of the secant is B times the whole thing, think add, so I have B plus C. Set that equal to the tangent squared, and our tangent has a label of A, so I'm going to have A squared. Okay, so those are the two formulas we're going to be using to try and find missing lengths. Okay, so for number four, we have two secants. So if I'm thinking outside times the whole, maybe let's start with this bottom one since we have some nice solid numbers to work with. So the outside is 2. The whole thing we're thinking added up, 2 plus 4. Okay, go to the top. Outside is x. Whole thing added up, x plus 1. Okay, so now we have an equation and we can solve. So we have over here 2 plus 4 is 6. And with this, we want to think distribute to both parts. So I have x squared plus x. Okay, so simplifying, I have 12 is equal to x squared plus x. All right, in order to solve this, we're going to have to do some factoring. And in order to factor, we need to get everything on the one side of the equation. And we're going to set this equal to 0. So this is going back to algebra for a little bit. We have to remember how to factor. So when we're factoring, we're breaking this up into two factors, where I'm looking for my first term. So my first times my first has to multiply to be x squared. So we know that that's going to be x and x. Now the numbers that we're looking for over here, we know it's going to have to multiply to be a negative 12, but it has to add to be a positive 1. So I want to think factors of negative 12. So factors that we have, well, we could do 1 and 12, we could do 2 and 6, we could do 3 and 4. Okay, sign of the middle term, which is positive, always goes with your larger factor. So I know that those all have to be positive. Now I want to say a positive times a what would give me a negative? Well, a positive times a negative would give me a negative. So now these are the combinations, but I need to find the set that's going to add to be 1. So it's not going to be this one, and it's not going to be this one. This looks like the set of numbers. So negative 3 times 4 definitely gets me negative 12. Negative 3 plus 4 would give me positive 1. So we have found our factors. Okay, and from here we have to solve for x, meaning I'm going to set them each equal to 0 and solve. And when we solve, we find x is equal to 3, or I find x is equal to negative 4. Now you want to look at your answers and think, can I have them both? Sometimes you can, sometimes you can't. We can't have a negative 4. And the reason we can't have a negative 4 is I can't have a negative distance. So I reject the negative 4, I keep the positive 3 and tell you that that value of x is just a positive 3. And this last one, number 5, we're going to solve for x, and it says we're going to keep this in simplest radical forms. So again, if I'm working with my secant, we know it's going to be the outside times the whole. To get the whole, we want to think add. We said with the tangent, I could either think again outside, which is x, times the whole thing, which is x, or I can just think tangent squared. Okay, so simplifying, 4 plus 9, we get 13. And if I multiply 4 times 13, I get 52. Now, we have to keep this answer in simplest radical form. So when I square root 52, what this is saying is I need two numbers that multiply to be 52 where one is a perfect square. And nicely, if I look up above, that's actually broken down for me. So 4 times 13 gets me 52. 4 is my perfect square. Keep in mind they each get their own little house. And then when we're simplifying the perfect square, square root of 4, we know that that's 2. That gets to come out of the house. Square root of 13 is an irrational number, goes on forever, so I want to keep it as square root of 13. And I found x. So now that's my simplest radical form for my value for that segment. Okay, we'll practice this more in class. I hope this helped. Hope you have an idea of the formulas, and have a great day.